Felix Hale, Vyat Reeves, and Moshe Razali, which came in 2 years back, 1909. The second is by Felix Hale and Tariq Anos, which they use these reparametrization modes to compute some 6-point conformal blocks. And recent work by me and Arnab Kundu and Patra from SINP. We delve on it a bit more. So I'll explain. First of all, I'll try to motivate why these reparametrization modes are sort of necessary in CFTs. So I'll skip the introduction first, tell you what reparametrization modes are, and then introduce how and why we need, like, sort of, so as to give you a better understanding of things. Okay, so I'll skip all these things and I'll start here. Okay, so the place where we would like to begin is the basic field of ADS CFT, where CFT is basically stands for the large N CFT with sparse spectrum, and we are looking for CFTs which are like whose dual is basically ADS physics and stuff. Okay, and basically graviton exchanges are the ones which are captured by sensor exchanges in the CFT. Okay, so yeah, G Newton basically scales with 1/c depending upon the dimension you're in. Okay, and we know that conformal blocks, the simplest one being that of identical scalars in CFT, 4-point function, can basically be written in this form, where you separate out the 4-point function in terms of 2-point functions, and whatever rest remains, it can be shown as a function of invariant cross ratios, and we are in D dimensions, okay? Not in any specific dimension. What can be used to describe this conformal block is a shadow operator. A shadow operator is a fictitious operator. If let's say if an operator has dimension delta, the shadow operator has dimension d minus delta. So this is the definition, and the way you define it is you define it via conformal integral. So to define conformal integrals, you need to go into embedding space, which you would not be doing. I'm just saying, just to introduce things here. And in this embedding space, you define conformal integrals by appropriate weights, such that you end up integrating conformal equivalent spaces and stuff. Okay, and you can define what a shadow operator is via using the weight of the operator as shown here, and of course you can generalize this to spinning operators as well, where what you use to describe spinning operators is the inversion tensor. Okay, so you have an operator O with spin L operator O with dimension delta, then you can contract all its indices with the inversion tensor and then define the respective shadow. There are various forms of normalization over here. I'll not delve deeply into it because it's not that relevant. Okay, so one can therefore also define an integral expression for the projector of states, which help you give the conformal blocks. Okay, using this integral representation. So a general integral representation for a conformal block of operator O can be constructed from O acting on the ket and O tilde acting on the bra. So it's a bracket thing, and you're conformally integrated here. Throughout the whole talk, I will basically be using this normal space-time integral to denote conformal integrals, but it has a technical meaning and you need to do that. The proper thing, and only certain kinds of conformal integrals are known in D dimensions. Okay, so there is a limitation as to how we proceed from this. But nonetheless, we can use this to get conformal blocks in any dimension for any operator, and provided you know what it is. But what it also does is that this definition 7, you can interchange O and O tilde and it will mean the same thing. It means that you are projecting onto states which are created by the operator and its shadow. So you need to factor out this shadow contribution. Okay, and the shadow is a fictitious person. Its dimension is negative, and it has a peculiar behavior in the sense that when u tends to 0 and v tends to 1, where u tends to 0, v tends to 1 is basically like the S channel, where 1 and 2 come close to each other, 3 and 4 come close to each other. So the 4-point function should basically look like a 2-point function. Okay, and it would have the wrong behavior. So the wrong behavior over here is captured by the shadow, and you should sort of filter it out. Okay, this is done in d-dimensional CFT. This would be done by some monodromy techniques, but in 2D CFTs, where we would be interested in the bulk of the talk, this is simply done by imposing holomorphic factorization. This is the beauty of it.
Rohan?
Yeah.
So I just want to try and understand the shadow operator a little bit. So the block itself is the contribution of a Verma module to the 4-point function, right?
Yeah.
So what a representation theoretically, what does the shadow mean? Shadow operator, what does it signify? Or is it just a useful intermediate tool or something?
It is a useful intermediate tool, but if you're algebraically looking, it is just working with some other operator with a dimension d minus delta.
I see. Okay, so there is some kind of natural pairing given by you can go to the previous slide.
So if
okay, so
the definition 4, I think, is the easiest.
Okay. Okay, so there is some kind of natural pairing between this guy and
but if you're in the CFT and if you're asked like what is the 2-point function of the shadow, given that its dimension is d minus delta, 2-point function, 3-point functions follow the generic rule. You simply go ahead and use it. Interestingly, and this is relevant because I think like a month ago or something, in celestial CFT, people were talking about 2-point functions being delta functions. I think Shubham was asking what was going on over there. The 2-point function of the shadow with its operator is actually a delta function, and it is conformally invariant.
Yeah, that's why I was a bit confused actually, because he had, I think, like the 2-point function of a 2-point function of the so-called prime is to be delta function, which is weird. But
so it's not, because there is the bra and the ket contraction is positive only when there is some sign difference between their weights in that celestial CFT.
Okay.
Like it has to be plus V and minus V or something like that. But nonetheless, if the weights are different, like as in the case for O and O tilde, the 2-point function of O and O tilde is a delta function. It's not 0. Okay, and it's conformally invariant. It has to be a delta function to be consistent with this definition 4.
Okay,
and other things. Okay. But that's basically the only thing. And apart from the states, it's basically you say that it creates certain states and it annihilates certain states, but at that level, if you look at the unitarity aspect of it, it would be non-unitary because it is negative dimension.
Okay.
So that's it. And basically, at the end, you have to get rid of this shadow operator. It's called the shadow block. The shadow block is basically the fictitious block. Restricting yourself to the operator block is basically termed as restricting yourself to the physical block. So it's the physical thing, terminology. And in 2 dimensions, that if you simply say that you impose holomorphicity, like if you're looking at the left moon sector, everything depends on Z, and likewise on Z bar. You basically have eliminated the shadow contributions. In 2D CFTs, it's quite simple. Okay, you don't have to do.
Yeah, I didn't understand the connection between the shadow operators and conformal blocks. Like what was 7 and.
So the left hand side of 7. This is basically can be used as a projector for states which are propagating, which are generated by O and O tilde. So so this is basically a stand-in for this integral is basically a stand-in for states generated by application of O.
But it's only going to, so it's the left hand side of O, when let's say that acts on some generic state, right? it's only going to click with states that are generated by O, right?
Yes,
or
that's
the
why it's a
states in the
projector.
O family.
Yeah.
Okay, so this is basically a map from the module to its shadow module or something.
So you can check that if you square O, it will give you O again, and yeah, if you square O, you will get O back. And so basically, how would you write this projector O over here? Generically, you would have written it as O acting on vacuum and the raising operators acting.
Right.
So it's all the states, and you restricting it to that, right? This definition 7 is the analogous definition in integral language. Okay, so it is the O operator acting on vacuum and O tilde on this side, but instead of the summation, you have an integral. Summation over all the raising operators acting on O acting on vacuum. Instead of that, you have an integral. So this is how this conformal integral replaces the sum, which is the raising operator acting on it. So all states generated by O are L minus M. Oh, sorry, not L. L minus acting on O acting on vacuum, and then you have to sum over all these states.
Okay.
That sum is being replaced by an integral. So it is of that form, and this basically plays the role of the projector. Yeah. So that's basically it. Yeah. But in order to prove more deeply as to why it should be a projector without showing that it is it basically yields results which is this thing to similar to that of the known answers doing the sum method. That I do not know exactly how to do.
Yeah, I mean, I can see that it's sort of, because you mentioned the thing about delta function normalization, I can see that it squares to itself, right?
Yeah.
So it's a projector.
Yeah. And it projects, I mean, by its nature, it projects onto both the states generated by O and O tilde.
Right.
So it's like not just O, but also O tilde, but that O tilde you have to factor out. Yeah. Throw it away, whatever that behavior is. Yeah, which is quite difficult. I mean, you have to difficult in the sense you have to use the monodromy technique of how things behave close to how things behave when you take operators close to each other, their expected behavior using what's it called, factorization and stuff. The shadow block will not obey that, so you have to get rid of that. That's basically. Yeah, it's a bit indirect. I agree that you replaced the sum over states, the basic definition of a projector, which sum over states with an integral. There is no direct way of seeing this. Yeah.
Cool. Right.
Yeah. So okay, the shadow operator formalism, as I said, is useful in getting global conformal blocks. Global conformal blocks, the word which is always used when you're working in 2 dimensions. So in 2 dimensions, what happens is you can generate states from the Virasoro descendants also, the full Virasoro, not just the global part. And till now, I've been talking about D dimensions. So this integral basically works the way it does is if you're playing with this integral in 2 dimensions, using this integral in 2 dimensions, it's important to remember that you can only get the global blocks, not the Virasoro blocks. And as I said, CFT has Virasoro contributions, which are basically the physics of as you will see, graviton back reaction and asymptotic symmetries of ADS and stuff, of BTZ and stuff, and all the things. Okay, so let's play around with this and proof of concept as to how and what do these integrals give us. So let's take the stress tensor, which is a spin 2 operator of dimension D. And its shadow is basically constructed by contracting with the inversion tensor. Okay. Again, just to remind, the indices, you need to actually work in embedding space to do any of these things, but we'll abuse notation left, right, and center, and just write everything in. So it turns out that the shadow operator can be written as a total derivative. Okay, shadow operator of the stress tensor T tilde can be written as a total derivative of some other operator. Now the shadow operator of the stress tensor has dimension 0, and this other operator epsilon, which we will end up calling the reparametrization mode, okay, that has a dimension -1. So this is even more fictitious. It's not there in the theory. Okay, and this P is basically an object which makes it symmetric and traceless. You can just forget that. Just remember that T tilde is just del mu. It's a derivative of, it's a descendant of epsilon. Okay. Now the 2-point function, as I said, of T tilde is directly deduced from global symmetry principles. Okay, and since its dimension is 0, you only need to take care of its vector indices. So the 2-point function of the shadow of the stress tensor is just product of inversion tensors. And with a bit of jugglery, you can write it as total derivative with two derivatives outside. It turns out that epsilons, which are the which we call reparametrization modes, are basically have a 2-point function of this form. It goes as x square log x square, where mu is something that has been made to take care of dimensions, but actually does not play any role in the theory. Okay. Of course, because epsilon itself has indices, you need a inversion tensor to go along. So it's inversion tensor times x square times log of x square. And CET over here is basically keeping track of the charge of your central charge of your CFT. Okay. How can we then look at what is the vacuum block of or the stress tensor block of I should not have called it the Virasoro block actually. This is just the stress tensor block because we are in D dimensions. So the projector is written as T tilde acting on ket and bra acting on this T mu. Okay, and you have integrated over xi, and you can clearly see that T tilde projector is the same as T projector, which is same as T square projector. Now what you can do is
why is that? Why is that? Why is T tilde same as T?
T tilde is same as T because you can basically exchange T and T tilde and it will have the same effect in whatever you insert this T in.
Is that only for stress tensor or generally for any operator?
Generally for anything.
Okay, okay.
So we can square the T projector, and what you will get is a double integral as you can see in the second line. Okay. Now what you can do over here is shift the derivative of T tilde, write T tilde as a derivative of epsilon, and shift that derivative of epsilon onto the respective T's. Okay, do the total derivative thing. What you get in turn is something like this. Now the plus sign in between is basically like there are two different projectors. Okay, the first projector in the last line, in this equation 13, is like divergence of epsilon, and the other guy is trace of the stress tensor plus epsilon mu del mu T. Okay, so this basically tells you that you can use the Ward identity of the stress tensor to get rid of this integral. Okay, and
Rohan,
yeah.
Can I just ask what serious problem you have with using the vert symbol in LaTeX?
Vert symbol. What is vert symbol?
The thing that a bra has, like a bra and a ket both have like a left hand side.
No man, it will become so it will become two. What's it called? Zero डालना पड़ेगा and it will become like.
Oh God. Okay, fine. All right.
I know. It's only this expression which is causing this kind of an eyesore or confusion, but there are no such expressions.
All I'd like to say is that civilization has moved on. You should join us. Like,
I mean, civilization should catch up to this, I would say.
Oh God. Okay. All right. Sorry. Move on.
Yeah. So because it's open, because anything can act from that. So I don't see why you should put a word over there. Anyway, so this is what you get. So you can get rid of this integral by using the delta functions that you get in the Ward identity. That's basically the idea, that this conformal integral can be gotten rid of by using the Ward identity delta functions. Okay, so basically what happens is if you take I don't know why I've written Virasoro everywhere. It's not Virasoro. It's just as a conformal block. If I act on it this projector on like V1 V2, then this is what I get, and you can clearly see that we can use the sessions Ward identity, d-dimensional. This you can tune your Ward identity to look like this, as that the trace part vanishes always. Okay, which is useful if you're doing like 2D CFT, because there is no trace part of the stress tensor by definition.
Sorry, I'm slightly confused. Like if you had started with the original definition for T tilde, you would have got this derivatives hitting on B's, no?
Derivatives hitting on T's.
V1s and V1, V2, yeah.
That will happen now. So the derivatives will hit on V1 and V2 because of the Ward identity.
This is I thought this expression you're using in 14 for T tilde came after you did some by parts manipulation and so on.
Yes, I did that. But even if you do, I mean, you just end up using the Ward identity.
You're saying even if I had used the original expression for T tilde, like I wouldn't have got any derivatives on V1s when on the way to 14.
No. You will get it. I'm saying.
Okay.
You will get derivatives on V and V. As you can clearly see, is the case that you end up getting. In the sense that it will factor out. You can write it out and it will factor out. You use the particular form of you use the particular form of the 2-point function to know what its value is when derivatives act on it. That is how.
Can you go to the previous expression? I think that might clarify.
Yeah.
So Akhil, what's happening? Equation 13, right? The last line, right? Just think of that whole thing as an operator. Now you're acting it on V1, V2, right? And then you get term by term, like what he wrote on the next slide.
Yeah. I thought if I start with first line of 13 and hit on V1, V2, like even by the time I reach last line of 13, I would get derivatives on V1 or something. Some by parts manipulation went on between the second line and third line of 13, right?
So just hold on. V1, V2 have different coordinates. They are not the coordinates which are getting integrated.
Oh, okay.
Psi. So the derivative when you
right.
That's total derivative. It's just that.
Okay, thanks.
Track of it will get. There is another way of doing it. Either ways, if you just do it, you'll end up with the same answer. It's not something. But this is an important part that these authors noticed in the first paper, that you can actually write it like this, and we've basically gotten rid of the what do you call the conformal integral delta function. Okay, in d dimensions. Okay, and this basically seals the deal, and basically the whole paper is just talking about how we can do it. And so, okay, so you use this Ward identity, and this B12 is in 14 is basically this guy here in 15. It's going to play a major role, and I'll tell you why there is an index 1 on top of it and blah blah blah. But this is what it is. Okay. And so the stress tensor conformal block looks like this in any dimension. Therefore, you have a nice closed answer, because B is basically a bilocal, but it's linear in epsilons, and you know what is the 2-point function of epsilons. Okay, and so you get a nice expression for the stress tensor conformal block, but it turns out that you only get expressions for even dimensions. For odd dimensions, it vanishes, and that's because, it's because this has something got to do with the anomaly associated with conformal transformations, and this anomaly action vanishes in odd dimensions, and therefore you cannot capture it. I do not understand more of the detail exactly how that sort of turns out. But if you try to write an effective action, which we will do for these epsilon modes, it turns out that it effectively vanishes for odd dimensions. And the way we write it out is basically saying what is the effective action such that its 2-point function is what is the epsilon's 2-point function. That's one way of writing an effective action. And so this is what it is.
This is the entire stress tensor block, right? Without any approximation.
Yeah.
16 and 17, right?
Yes.
So, like we know that the light cone blocks are known in every dimension, be it 3, 4, odd, or even. They have some universal behavior. So, you're saying that d equals 3 vanishes, like in d equals 3, equation 17 or 16 vanishes, right?
No. I'm not saying that. I'm saying this expression holds only in even dimensions. I'm saying the anomaly action that you would be writing down using this cannot be written down in odd dimensions.
Anomaly action.
I'll write down an effective action for epsilons.
Okay.
And it turns out that you cannot write it for odd dimension just because it vanishes or something like that. I mean, I do not know more about it as to how exactly it works and stuff. But yeah, it's basically that anomalies don't exist in odd dimension or something like that in CFTs.
Okay. Just go on, maybe.
Yeah. It's a vague statement that even I do not know. So I'm not the right person to answer these things. Yeah. So so this in 2 dimensions basically looks like this. So in 2 dimensions, you simply you calculate this and keep a part which is only dependent on z, and there is a part which is also dependent on z and z bar. You throw that away. Yeah. And this is for those who have worked enough in 2D CFT. This 2F1 combination is basically a single graviton exchange. Conformal block that you get from the Virasoro conformal block that you get. So in 2 dimension, what happens is this integral captures single Virasoro exchange contributions. As if you acted once by the Virasoro raising operators and exchange these things. And this same answer is obtained from the usual definition of the projector to answer Nirmala's question why it should be same. So it is basically that it gives you the right answer at the end of the day. Okay, if you restrict to the physical block.
In the previous slide, you said that it gives the global part of the conformal block, right?
So in 2 dimensions, this is something interesting. So you can ask the question, what is it in the 2 dimensions? What is it doing in 2 dimensions? Because everything is
certainly not the global part of the thing. It has 2f1 squared, right? I mean,
exactly.
Z and Z. Okay. So somehow this gives the Virasoro part in 2D. Okay.
Yeah, it gives the Virasoro part in 2D, but again, you will see that there are. You will come to the 6-point conformal block. You will see something interesting happen.
Sorry, I'm confused about Shubham's question. I thought that like at large C, you only have the global part of the Virasoro, which is precisely this 2F1, right?
Well, I mean, global. Okay, I don't know.
In large C, you only have the global block of the. I didn't get it. What?
Yeah. I think that at large central charge, the only when you write down the conformal blocks, then the leading contribution at large C is only from the global part, right?
Global part, good. And this is the global part of the stress tensor. So this is simple, right? You take your stress tensor, act on it by raising operators.
Maybe I'm asking very stupid question actually. Like, so what I was thinking is that, like, since in higher dimension you get the global part of the conformal block. So suppose you are in d equals 4, you will get this 2f1z, 2f1z bar, and that combination.
Yeah.
And in d equals 2, you will get that same combination but with a sign change. Okay, but clearly that is not. I'm making a mistake somewhere. Yeah, so maybe my comment is not correct. Yeah.
No, but
I still don't understand. I'm sorry, Shubham. So what I'm trying to say is that Rohan said that this procedure accounts for the global part of the global block, right?
Right.
So I'm saying that in 2 dimensions, this is the global block. That's
true.
Why he's saying leading order in large C.
Yes, true. This is the global block, the global stress tensor exchange.
Okay. Okay.
Right?
Maybe we can discuss after.
So this answer is also obtained by acting simply raising operators, the Virasoro operators acting on the vacuum being exchanged by in your CFT 4-point function.
Right.
That's this expression is okay. So you use the full Virasoro L minus m L minus n because the global part of the vacuum is 0, right? So
yeah, because it annihilates the vacuum.
Yeah, it annihilates. So you exchange them. So you can. So this is basically the exchange of states generated by the full Virasoro acting once, like L minus m L. So it's just like 1 over C. If you act it more, the normalization in the denominator will go by C squared, and you can have more terms. But it's just the first level states acting generated by acting the Virasoro on the vacuum being exchanged, and that is what this thing captures. That statement is right. So how do you see that as so the statement would be true even if you said that if you took the stress tensor and asked what happens if you act on it by the Virasoro raising operators, right? So it will be like L minus 2 acted upon by L minus m, and that can sort of generate the tower of state. So you can look at it that way, look at it this way. The vacuum block is the same as the stress tensor. So this is what that answer is. So in 2 dimensions, the answer that it gives is basically what it tells you is there's a single level exchange acting on the vacuum. By level, I mean the Virasoro acting once, and that is what this answer is. Okay, single graviton exchanges in the bulk. Okay, and this is the one which is actually used to compute your chaotic behavior, because this is the conformal block. Once you've computed the conformal block into DCFT, you can play around doing this out of time ordering using this I epsilon prescription. And I will not bore you with these things. This standard practice these days. I mean, everyone know what this is. Like, you map the conformal field theory to a thermal field, to a thermal state by mapping the Euclidean time, and then you keep your Lorentzian times in a particular order, and your Euclidean time ordering tells you whether you're computing out of time ordered correlator or time ordered correlator, and then you take your t to infinity, which is the Rage limit, and so yeah, this is time ordering, out of time ordering, and it turns out that for time ordering, your conformal block goes as z square, so it goes to 0 as z tends to 0, which is the Rage limit. But for out of time ordering, you'll find that it goes as 1 over z. Z is the cross ratio, and which basically, after you've done the exponential map onto the thermal state, you'll get this 2 pi by beta behavior, the exponent. So that is basically the reason why this. So it's known that the conformal block directly captures the chaotic behavior, and what you have basically shown is that the 2-point function in 18 directly is the conformal block. So which is basically the 2-point function of epsilons, because this is basically the 2-point function of epsilons, and therefore epsilon sort of governs the chaotic behavior of. It's an effective description of chaotic physics.
Okay, Rohan, I don't know very much about this the chaos stuff, but I just want the sort of one-line takeaway from this slide. So the point here is that you can think of the stress tensor block as being determined entirely by like the epsilon 2-point function.
Yes.
Right. And then after that, you can do some I epsilon prescription and compute an out of time ordered correlator, which is relevant for chaos in some way.
Yeah.
Okay. All right. Thanks.
So we are trying to figure out what are the degrees of freedom which, So what is the operator which sort of behavior
responsible for
for chaos? Yeah. I mean, this whole procedure of doing chaos is just to see whether whether you have a chaotic behavior or not. But basically says that epsilon basically captures the effective soft modes of your theory. Yeah. So this is the reason. So let me go back and introduce.
Just wanted to ask, like, so you could have had like other operators also, right? And you could have gotten equation 22 corresponding to those operator
You
exchanges?
cannot write the shadow of other operators as total derivatives.
Oh, I see. Okay.
What about if your CFT had some conserved current? Would that be a possibility?
Yeah, for that you can do it. In fact,
So
those
even
authors are
higher
doing it for
spin
conserved current.
currents, right? I mean,
Yeah.
conserved higher spin currents, and like they would significant, like 22 would be 2 pi L by beta, and L keeping on increasing,
So
right?
those authors do it for conserved currents also in the same procedure, and it can be done and it changes.
I see. Okay. And so like so you are in your work, like you are assuming some sort of stress tensor dominance.
Yes. So
Okay.
it's holographic.
Okay.
We are not going into determining how that dominance happens.
Right.
We are assuming it happens. We are in the sector of holography.
Yeah.
So it's it's that. So let me.
Could you say again, why was it necessary for the shadow to be total? I mean, the stress tensor to be total derivative?
Because without that, what happened was the conformal block basically was determined by an integral. Okay, the way that integral went away is that you use some Ward identity, and the delta function of that Ward identity killed it. And that only happened if you could write the shadow as a total derivative. Okay, and so first of all, there has to be a Ward identity for that. So it can basically only happen for conserved currents, the stress tensor being one. And it so happens that you cannot take any odd operator and write its shadow as a full derivative. That doesn't happen. You can play around with it, but it doesn't.
So I'm confused. Was it because I wanted a Ward identity, or was it because conservation equation, or was it that I wanted a total derivative as the operator?
No, all these reasons are necessary. If one of them fails, you will not get to the end point. I'm saying any odd operator will not satisfy that. That's all.
Okay.
Okay, so let me start from the beginning, having told you what this is and where this kind of a thought has sort of originated from and stuff. So, yep. So as you know that scrambling is expected of large systems, and there are so-called fast scramblers, and black holes are the fastest scramblers, and they have a Lyapunov exponent. Shankar Stanford basically show that it is 2 pi by beta for let's say static black hole in 3 dimensions, and consequently there is a bound which is the MSS bound, and that any large and thermal CFT has to obey, which is bounded by its temperature. And for large and thermal CFTs with chemical potential, you have a slightly different bound, which was also observed for rotating geometries but only in 3 dimensions. After all this analysis of understanding of scrambling and out of time ordered correlations getting blowing up for black hole geometries, you had the SYK kind of plethora of work, which basically showed that the SYK model also has a soft sector which basically contributes to chaos, and this is captured by this Schwarzian derivative. It's like 1D time reparametrization modes which capture it. So you have a field theory whose soft sector is basically captured by an effective theory of 1D time reparametrizations, which is governed by the Schwarzian action.
So,
sorry,
Rohan, just wanted to ask, like, can like this the expressions that you showed for, like, say, the external scalar particles, have they been studied for external spinning particles, like stress tensor with a stress tensor exchange trying to compute the block in using, say,
you mean so you mean 4-point function of the stress tensor?
yeah, with a stress tensor exchange
in how many dimensions?
In, say, d greater than 2.
That is not done.
Not done. That's
I don't think
very difficult, I suppose. Is it? Like,
the last I know is an expression for writing that conformal block in 2 dimensions by Osborne, but that was like quite some time, 2012 or something.
that was some. I see. I understand what you mean. Yeah. Yeah. Okay. Yeah. That was d equals 2 actually. Yeah.
That was d is equal to 2. But 2 dimensions, anyways, 4-point function is completely
yeah.
fine. all endpoint functions of such tensor are completely known.
Yeah.
But why did you wanted to bring spin as such?
I was just trying to usually these the OTOCs of spinning particles are related to scattering of these states in some flat space limit, right? So I was just trying to see if somewhat, just some academic exercise.
Okay, cool. Yeah. Anyways, yeah. So coming back, the SYK model basically tells you that you have to look at 1D time reparameterization, which basically capture chaotic behavior of this particular Largen or family of Largen 1D conformal field theories. The bulk understanding of this was that you look at a black hole close to extremality. Its near horizon structure is basically governed by JT gravity, which is obtained by appropriate dimensional reduction to 2 dimensions. You use kind of a tractor mechanism and go zoom into the near horizon region of near extremal black holes, and you find that this JT action on shell gives you on shell in a particular manner gives you the fluctuations away from extremality, and that is captured by 1D time reparametrization of its boundary time coordinate, and it's given by the Schwarzian derivative. This was the understanding of it. Now we are in ADS. Okay. Now, so then, this particular fact of JT gravity, whether it captures the low energy physics, basically checked by Moitra et al. In 2 papers and Pranjal et al. This also checked for BTZ that really if you dimensionally reduced your root gr plus 2 lambda minus 2 lambda to 2 dimensions close to the horizon, you actually reproduce JT gravity, and that the thermodynamics of these 2 systems describe close to extremality match. Okay, and of course the Schwarzian basically tells you that if you consider the 1D CFT and whatever 2D ADS2, you could get the chaotic degrees of freedom. So what do these reparametrization modes talked about in this setting mean in terms of ADS CFT? Like if you have 1D reparametrizations in JT gravity, what does it mean from the context of ADS CFT, or what does it mean generally? Because if you're talking of these reparametrization modes, or which give the Schwarzian and whatever chaos and stuff, in the near horizon region, then they obviously do exist in the higher dimensional picture where you came from before dimensional reduction. So what do they exist there? What does it mean in terms of ADS CFT? What I just explained about reparametrization modes in D dimension and 3 dimensions should sort of convince you that that is the candidate that we should be looking for. It is basically the what you call the undimensionally reduced avatar existing primarily in the CFT. The description is as of yet known in the CFT, and which captures chaotic degrees of freedom. So that is basically the motivation. The fact that it was uncovered in this manner goes about because of a work by Kotler and Jensen. So what they did was they analyzed the coadjoint action of ADS3 gravity with appropriate Brown-Hano boundary conditions, which are relevant if you're posing Dirichlet boundary conditions and stuff. And they found that the effective theory that they get does not simply comprise of just the stress tensor, but it also comprises of a bilinear of reparametrizations. It's bilocal in nature, which is given by this. I'll explain what this precisely is, where f is your reparametrization. You reparametrize your 2D coordinates from x to f of x, and this kind of a bilocal operator sort of plays a role. And in what happens, this form would be used to compute the 6-point function by Anus and Hale, and I will explain where this thing comes from. So this particular insight of what reparametrization modes are again came from the BTZ analysis of much more thorough analysis of Kotler and Jensen in 3 dimensions, and which sort of underpins this kind of an evolution. That's it. Any questions over here?
I didn't understand the last part. So what should I take away from the last part that you said about
They did some complicated analysis, and they said that all nonlinear Virasoro contributions to conformal blocks, blah 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 blah, are captured by this effective action of ADS3, which are written in terms of not just the stress tensor, but also in terms of these kind of bilocal operators.
But then you mean that it's not just stress tensor dominance, it's something else also.
Yeah, but these guys, as we have shown, as I will show, is actually related to the stress tensor. They are actually related. This B is basically related to the reparametrization, and it sort of captures this contribution, nonlinear contribution of Virasoros to all conformal blocks that's what it is. And they use it as a leap of faith. It's not like completely proven, but like it works. And what we do is sort of show that it can be, you can actually test it without using this kind of a hypothesis. But nonetheless.
But just explain to me. Like you can do an independent CFT calculation where you construct the T tilde shadow operator, sandwich it between two.
That doesn't require any of this.
Yes.
Yes.
And you find that whatever you get as a result of that is equal to if you consider BH12 to be like this.
Exactly. I'll show where that equivalence comes. So I've just given this last point as basically a heads up to go and read up Kotler and Jensen, and it's a bad idea because it's a very complicated stuff. So it's fine. But it's some analysis that was done in 3 dimensions, which sort of pointed the direction towards exploring reparametrization modes in CFTs. Because this kind of an analysis, that's what it is. So let me go and proceed further. Okay. So we can write a generating functional. So this is a tangent, and we will not be pursuing this idea further than this point. We can write a generating functional describing the Euclidean CFT path integral for epsilons in this manner. That you have the SCFT, you have it's a path integral, and you have a source for your stress tensor, and you have so you have the source for the stress tensor, which is given by variation of your metric, and the variation of the metric can be written as del mu epsilon nu symmetrized. You can expand this to second order in epsilon, and this turns out to be something like this. So you expand this to second order in epsilon, basically implies that you use the fact that when you differentiate 23 with respect to G mu nu, you end up getting 2-point expectation values of your stress tensor, and that can be rewritten that way. You can use the definition of T tilde to rewrite this W2 in a much more eliminating manner, if whatever this is. I do not know why I put this slide over here. I can't explain anything of this. Sorry. It basically says that the effective action for epsilons can be written in a concise manner in this 26 form, and the authors. This is the work by Anus, Hale, and Hale, Viatreeves, and Rosali. They say that there exists an effective action describing these epsilon modes written in this 26 form, and so basically you can get rid of the there is a way in which they say that you can get rid of the shadow operator dependence by doing some gauge fixing and stuff, but those are just words. They have not developed that formalism better. parameter. So for all intents and purposes, just forget about this slide. I have not read it up to talk about it more. But you can basically describe.
What is the SCFT? Is it some free theory? I mean, from 23 to 24, you would need some expression for SCFT or no?
No, so this is just expanding it. So from 23 to 24, what you basically need is an expression for the 2-point function of your system, sir. And that is basically what you need. You're just expanding it in. That's what I understand from this line. You're just expanding it in second order. It's just some generic CFT, because you will be differentiating to expand it in powers of epsilon. You'll be differentiating with respect to g mu nu, and that basically ends up giving you stress tensors. So all you need is a stress tensor 2-point function. Basically that. So what 26 gives you is basically an effective action, which if from which you can deduce that the epsilon has a 2-point function which you already know of. It's in that sense that is an effective action. It's an effective action for homilies and stuff. But yeah, this formalism has not been developed or pursued, and we would not be needing it. This effective action business of.
Okay.
And you can just forget about this slide. Actually, should have removed it. Yeah. So let's stick to 2 dimensions from now and just start computing stuff and see how things are related. So in 2 dimensions, your shadow definition is basically this shadow of the stress tensor, which implies that the projector looks like this. It's just t tilde and t with 1 over c sitting outside. Okay. And there's a straightforward relationship between t tilde and epsilon, of course. There's a derivative involved, and we have written everything in z bar coordinates. So t tilde is basically c times del bar of epsilon. Okay, there's also, this is the holomorphic part, there's also the anti-holomorphic part. The important point to note here is that you need to have z bar dependence, otherwise you cannot define the shadow. Okay, this is something important. Okay. Correspondingly, what happens is that you can also show that the stress tensor is a descendant of epsilon, and you can show that in 2 dimensions it's just like del cube of epsilon. And this is a straightforward exercise. You can play around with these definitions. I'll not go into it, but you can also show this. The basic standard definitions of T and T tilde. Okay. It turns out that the 2-point function in turn of epsilon is constrained by these 28 and 29 to follow these relations. Okay, as I had already said, that t tilde and t basically ought to be a delta function, which basically also constrains your 2-point function of epsilon. Note that the 2-point function of epsilon has both holomorphic and non-holomorphic.
Rohan, can you just explain, like, how did expression for t come about? I mean, are you assuming any 2D CFT?
No. It's not. You're not assuming anything. You can show this. So you can show this by using definition 27. That's it. By writing. So you can exchange t and t tilde. So if you want.
So either one has to be the input. Either t tilde has to be the input, or t has to be the input, right?
So so this definition is the input.
No, okay. But using this, how can you determine both t and t tilde?
No. See, so you use 27 and 28 and you can.
So 28 is the input. So how did you get the t tilde in 28?
How did I get the t tilde in 28? This is the same old definition that you can, in any d dimensions, I can write t tilde. I can write 27 as a total derivative.
I see. I understand. Okay.
Yeah, it is just playing around with these basic things that you can. And in fact, you can notice a very nice thing that this 27, this integral over here, the kernel of this integral in 27 for t tilde. This kernel is basically the 2-point function of t tilde.
I mean, I could have also started with given 29 and using 27, gotten 28, right?
Now, I think you can, yeah. I don't directly see it, but probably you can, yeah.
But in what is what is the CFT in 29? Like in the sense that
No, this is just basic principles of CFT. We are not using anything more, just conformal invariance.
okay.
Nothing more. I'm not. Yeah, this is not something. Yeah.
Okay. I'll try to think. Yeah.
Yeah. So yeah, there are some basic algebra that can give you this. It's nothing profound. Okay. So the other way of finding what I was saying was, given these relations, the other way of which basically stem from this definition 27. So 27 allows you to write down t tilde as a total derivative, which then again can be used to figure out what t is in terms of epsilon. It just so happens that you can write t as a total derivative epsilon, some kind of a cubic derivative epsilon, acting on epsilon. An expression for this exists in general dimensions also. And it will be complicated projector structure in front of epsilon, but nonetheless there will be like some amount of cubic or whatever derivatives acting on d minus something derivatives acting on epsilon. So the stress tensor can also be shown to be a descendant of epsilon. That's the crucial part. Okay, and these relations can be used also to determine what is the 2-point function of epsilon, because they basically constrain how things have to look like. So t tilde and t have to be a delta function. A t 2-point function have to be a power law. So that can basically tell you that again consistently you'll find that the epsilon 2-point function is basically this.
So something like 29 is true in general dimensions, where like
yes.
that the stress tensor is a descendant.
Yeah, can you see 25 over here?
Right. Thank you.
That is. We can use these kind of definitions and stuff. Yeah. Sorry. Yeah. So you can basically use these to to figure out what is the 2-point function of epsilons. Okay. And it gives you the right answer. So this is a right way of working. You can get differential equations and then you can solve them and then you can get this answer. Notice that epsilon 2-point function, although it's the holomorphic part, also has z bar dependence. This z bar dependence is important because otherwise you will not get this delta function, for instance, in 30. Okay. So the 2-point function of epsilon has this z bar dependence. Of course, if you want to restrict to the physical part, then you throw away it's an additive piece, z bar dependence, and you insist on holomorphicity and you just keep this guy. Okay. Now what we want to compute is basically the star channel involving three light operators in 2D CFT. They combine in a manner in which they exchange the stress tensor. The star channel is basically just that. For example, in the left hand side you can see the star channel as against what is the comb channel, where you are exchanging the intermediate is also some kind of a light primary and not the stress tensor. Okay. So what we'll basically use is the above machinery we had just sort of developed to understand what is the 6-point conformal block of like identical light operators. And we would see the 1/c expansion of this. And the reason why we would want to do that is because you can have a kind of out of time ordering which yields a scrambling time which is twice the scrambling time of the 4-point function. So it's an even more fine-grained measure of chaos. Okay, so that's one of the reasons, but we'd like to investigate how these modes sort of work out and stuff. Okay. So Anus and Hale basically make use of some kind of a nonlinear reparametrization mode business, which we'll go into and explain further, and we'll get that how this produces a 1/c squared subleading order effect in the computation of this. Okay, we would basically try to understand by making use of first principles, not using any fancy nonlinear stuff, and just the word identity, and we'll try and get the same result. Although we do not get the same result because we I was lazy and I didn't compute exactly the same quantity, but it's basically the same quantity. And as far as observing chaos and all those things goes, it produces the right result. So this is basically it, and it's basically buckle up and some boring computations ahead. So yeah, so let's look at the star channel. It basically looks like so you have three pairs of operators, phi1, phi2, x3, x5, y4, y6, and they are all fusing to form these white lines assistance exchanges. And the way they've written the assistance exchange is they've introduced a TT tilde projector between each pairs. So this is how exactly they evaluate it. So it's phi1, phi2 fused to give T0 and like T0 tilde, x3, x5 fused to give T3 prime and T3 prime tilde, y4, y6 fused to give T4 prime and T4 prime tilde. And you have to integrate over all assistance exchanges, and you have a 3-point function of T tildes. Okay, so this is basically the global block that they wish to compute. So when they went out to compute this thing first, they thought that they should give the exponential behavior and stuff, but it'll turn out that it's not the case. So, yeah. So I'll skip the details about like how do you do it, how do you sort of go from 32 to 33, but it's exactly the same step that you did for the 4-point function. It's exactly the same repetition. Okay, and what you end up getting is all these 3 delta functions go away because of the 3 word identity which is used 3 times. Okay, and you end up getting expectation value of 3-point functions of P's, and this is called the 6-point star channel. Okay, so all you need to do is compute 3-point functions of epsilon in order to compute something like this, because this will involve 3-point functions of epsilon. And the 3-point function of epsilon is some complicated beast which is not that easy to compute from this differential constraint which is written over here. Okay, but nonetheless, go ahead.
And this is true for any dimensions, or
no, this is all in 2 dimensions. Now we are in all 2 dimensions.
Oh, so now this equivalent of this integral has or can't be probably done for higher dimensions, is it?
Just hold on. No, you can do it in higher dimensions. You can do it in higher dimensions because you're simply using word identity.
So like okay.
Yeah, till 33, it's all you can do in higher dimensions, and you're using word. When I say word identity, I mean the derivative word identity.
So equivalent result for closed form result for equation 34 can be found, you're saying, for higher dimensions?
I mean, it was quite a headache to find it for 2 dimensions.
Okay.
You can find it for higher dimensions also.
I see.
Yeah, I never knew what these lithium functions were before. So that's fine. Yeah, you can use it.
Lithium functions.
Yeah, this is a very.
It's polylog. I mean, I was trying to solve some differential equations, and I didn't know the answer is this. So if I plugged it in, it would have solved that differential equation, and it's a special function that you didn't know existed. So it's like, what is what mileage do you get by writing?
Look forward to your next paper where we'll have beryllium and all the other.
This is weak. But look at so this is the point, that these guys basically thought that you can do this trick and get it, but it turns out that this by itself does not produce any out of time ordered effect, not even the simplest one. Okay, forget like twice the scrambling time, kuch nahi produce karta hai. And this is not, however, this is not even the only contribution. You have missed out one contribution which actually comes from nonlinear interactions of epsilon.
I am a bit confused. Like, what do you mean by OC behavior? This is a 6-point function now.
This is a 6-point function. So now you can do all sorts of out of time ordering, right?
So okay. So they checked every one of them.
Yeah. So I'm not going to explain. I don't know why, but lack of time or whatever. So there are let's say 2 endpoint functions. When n is 2, you have this 4-point function, right?
Yes.
And you have this out of time ordering. But if you have 2 endpoint function, you can have many ways of out of time ordering. There is one way of out of time ordering which is called like this braided out of time ordering, which basically means that you arrange all the pairs on in a line, and next to the nearest neighbor are out of time ordered.
I see. Yeah, you can have many orderings like in
Yeah.
6
So
point
this is
function.
the simplest. It's called braided, but the simplest way to see it is you arrange all these pairs on a line, and the nearest neighbors are out of time ordered. This kind of time ordering produces if the CFT or the whatever QFT is chaotic, it produces a exponential growth with a scrambling time which is n-1 times the 4-point function scrambling time.
I see.
And therefore it is the even more fine-grained version of chaos. So it's lasting for like n-1 times t star and stuff.
I see.
There's just some detail, but yeah, there are some nice papers.
And this three. Sorry, go on.
Yeah, go ahead.
This 3-point function you're saying doesn't produce anything, like any ordering doesn't give any exponential growth.
This expression, the first expression that was computed, or like expression 33, that does not give. Okay. So actually, what has happened is that in the first subleading order, so what you're doing is you're in 2D CFT, okay, and we have light operators, and we're computing the conformal block. So the conformal blocks the vacuum block contribution follows like 1 over c squared. The first contribution you can show for such a star channel comes at 1 over c squared and not 1 over c. Okay, and this is not the only contribution at 1 over c squared. That is the point. There is another contribution which this kind of a naive way mixes. You might think that this is the right thing to do because I can always decompose things into like 3-point functions in a CFT and get the answer. Okay, but you have missed something over here, and the way that is fixed by Anus and Hale is a very non-trivial thing. So that I'll go to next. Don't ask me why it works.
One more question, like
okay.
Like why do you think that OTOCs or any ordering of 6-point correlators will show exponential behavior? Like for 4-point functions, I understand there is like you have this map by from Aldacena, who mapped it to a 4-point Regge limit or out of some Lorentzian limit of a 4-point function to commutator of 2 operators, right? Why do you expect a 6-point function to show exponential?
You can do the same things for 6-point functions. You can do the I epsilon prescription for 6-point functions, which I'll show you.
Okay.
Exactly the same thing can be done, and you should expect the same thing. And and it has also been shown that this kind of a prescription for I think Felix Hale, Loga, some of them have papers on these things. I think there is a Hale Rosali paper on it, and also Loga's paper on multi K-point out of time ordering showing chaotic
behavior. I see.
They talk about reparametrization and stuff, but there is this chaotic behavior also there for endpoint functions.
Okay.
Yeah, basically they map OTOs to various nested commutators.
Yeah,
that's what they say.
Yeah.
I see.
Isn't there a limit where such that this 6-point function will essentially be some sort of 4-point function?
Yes.
Limit.
Then it's obvious, right?
Yes. That's also there because what I can do is phi and y I can do out of time ordering. X is just a spectator. Okay, it's there. And then what Anurag is saying is that now I can do a what's it called, cluster decomposition or whatever, and take these x points very by translation or relation. But that is basically that's basically a symmetry. So it should not matter, but I know what it means. There should be an exponential behavior concerning this, and it gives you T star. So there is all the reason to expect it. That is the answer.
I see. Yeah. Okay. From 4-point. Yeah. If you think like that, okay, I agree. Yeah.
Yeah. That should be. But this point of maximally out of time ordered. Maximally out of time ordering, which is there, which involves all the operators. That is very special to whatever endpoint correlators. That so this particular guy would be there is a time ordering which basically the x and phi are out of time ordered, phi and y are out of time ordered, but x and y are time ordered. They are not out of time ordered.
Okay.
So it's x, phi, y, and this in a large N CFT, holographic CFT, blah blah blah, should show you should have a scrambling time of twice the 4-point function scrambling time, and this has been shown. I mean, this is like more than enough papers that have been written on this. This has been even shown probably for SYK and complex models and stuff, that people have played around with this. Yeah.
I see.
Yeah, so this is part of literature that I'm not covering. Yeah. So yeah, this is coming back, they do this, and this simple argument does not give you the answer because there is a 1 over c square effect which has been ignored, and the way they fix this ignorance is by doing shady business. The shady business is 35, and they say that this 6-point conformal block is basically given by this kind of a function. So I'll just go into it. What it is basically a 3-point function. In the numerator, if you see, it's a 3-point function of b's, then divided by the 2-point function of b's, all possible b's. Again, divide the whatever denominator by this. So it's in the numerator, it is the 1-point function of b's and the physical part of it. Okay. Now you will ask, what is the 1-point function of b? Because that is just epsilon, and epsilon ka 1-point function 0 hai. That is not the case. Okay. This b is not the same as that b. This b is the non-linear avatar of that b, and the way you argue that is say that let's assume you are changing your coordinates from z to z bar, the z to f of z, but this f of z is function of both z and z bar. It has to be, and this epsilon is the infinitesimal parameter. Okay. Then what you can write is this b can be written like this. This is the definition of b, 37. Okay. If you look closely, what 37 is, it is basically it's basically the ratio of a 2-point function of scalars in 2D CFT in 2 different frames. So it is z12 to the power 2h divided by f1 minus f2 to the power 2h, and this guy in the numerator in 37 within the brackets is the Jacobian. Okay, and it's the generalization of this to not just include z but also z bar. Okay. This is what is coming out of Kotler and Jensen, and these people take it. They say that this is going to capture all Virasoro contributions, therefore it should also capture the missing part which was there in the last paper. And what that d1 that we were talking about is that you expand 37 using 36 in powers of epsilon, and the first guy that you get 1 plus is b1 of 1. Okay, that was your b1. You can prove it perturbatively, and you can do this. So the idea that they say is like, look, I mean, they don't even try and motivate this. Okay, I'm not kidding. So they say like, look, if you want to get Virasoro contributions at a nonlinear order, we are inspired by work of these people. So we will use 35, and you plug in, expand it perturbatively, and basically compute compute 35. Okay. Note that we want to, yeah.
Sure, God.
No, I was just asking, like, what is the check for such a, because as you said, 35 is some ad hoc.
I mean, check is what I did. So yeah.
Okay. Cool. Rohan trying to be very modest. Yeah. Okay.
No, I'm not trying to be modest. I tried. See, it's not that I knew about this 35 thing. I was doing things independently. But then when I was reading their paper, they wrote their paper saying that they're doing this conformal, they're finding this conformal block, and they're putting it to use and computing something. Out of middle of nowhere, they're using this thing.
Right.
And I'm asking, where did this come from?
Yeah, of course.
And there is no justification for this. Okay. And the fun begins over here that B12 is the function of both Z and Z bar, And so you say that you do the computation. At the end, you get the conformal block, and then you restrict to the holomorphic part, and that's how you get rid of this ZZ bar dependence. Okay, so it's a very contrived, it's a prescription. It's not a formalism as such.
Yeah, that looks to be the case. Yeah.
And this kind of a normalization can take you for a ride, because if you start expanding, it becomes really complicated. So what they do is they precisely expand 35.
I have a question. So just to make sure I'm understanding what is happening. So the statement of the last slide was that, like, if you just calculate the 3-point function of the t tildes or something, you wouldn't capture any out of time order correlator because you are missing on the some way sort of block contribution.
Just at the level of conformal block, I mean, just forget about just OTO or whatever. Just at the level of conformal block, there is a contribution which has been missed by that computation. 35 captures the entire thing, so it will also capture that and some additional effect.
And
at C squared order.
What's the analogous statement in higher D?
Well, in higher D, all these complications don't happen. In higher D, I think that's the only answer, because there is no Virasoro and
so
stuff.
If I'm doing gravitational bulk calculation, what's the statement? In higher Ds, I just need to calculate simple graviton exchange in the bulk. To get the OTO, but in 3D, I have to do something more specific in the bulk. What is the statement?
Sorry, you're in higher D. Like greater than 3 dimensions in the bulk here.
Greater than 3 dimensions, I can do a gravitational backtration calculation and I'll get the OTO. But in D equal to 3, what is the statement of this 35? Like, what is the additional thing I have to do in the bulk? Or is that even the
is 3 in the bulk, right?
Yeah, I'm just asking what is the meaning, what does this correction mean in the bulk for D equal to 3? D equal to 2, ADS 3, sorry.
So what does it mean? So this is explained in Kotler and Jensen. They arrived at this 37 form of B by analyzing the graviton ADS3 root GR gravity action and doing coadjuvant orbit business. So what it would mean in the bulk is some kind of Brown-Henu kind of diffeomorphisms in the bulk, and this is their nonlinear action.
But I thought naively the diffeomorphisms were captured by that this T tilde analysis you showed in the beginning.
That's in the CFT. That's true. But in the bulk,
but for the 3-point functions, you're saying that's not enough. But in the bulk, there's no subtleties. You can just do a.
It is related. All these epsilons are related. So this B is nothing but comprised of epsilons, which are basically comprised of T tilde. And I'll show that if you basically made use of the word identities, you don't have to use any of these things, and the analysis looks much more simpler. So just hold on.
Okay.
So everything can be explained just by using T and T tilde. That's it. That's all I'm saying. You don't have to use this kind of jugglery. Okay. If you need a simpler answer, it should be possible to see everything in terms of T and T tilde and stuff. Yeah, that's the whole point actually.
Okay.
So this is what they compute, and they expand 35, powers of 1 over C, and it turns out that this is what you get. You get 1, which is just the product of the 3 2-point functions, plus the star channel that you had computed, and this kind of beast, where 2 lines sort of go and contract with phi. This plus permutation is basically permuting phi x and y in a symmetric manner. That is, they call this U star, and they compute this by perturbatively expanding that guy. And all you need is the 2-point function of epsilon, and they simply spit out the answer. Okay. Now this particular U star UT is that basically has all the feature, and actually shows this Lyapunov exponent to be 2 pi beta and the T star to be this. Okay. Now that's their story, but we can compute the star channel conformal block by simply using Ward identities corresponding to epsilon insertion. Because it's 2D CFT, so everything has to be constrained by just Ward identities. When I say Ward identity, I do not mean the derivative Ward identity. I mean stress tensors, 2D stress tensor being inserted in any correlation function. In 2D CFT, it's completely not in t-dimensional CFT. So let's proceed with that and see if there is a simpler way of doing this.
So one can, you have 15 minutes left.
15 minutes में कुछ नहीं होगा.
So we'll keep all the questions till the end.
Yeah, 15 minutes is enough to explain. Actually, 15 minutes is more than enough. Actually. Yeah, so we can describe the star channel as follows. Okay. So basically what is happening is you write the 6-point function and you insert identity projectors or whatever stress tensor projectors, t tilde projectors between each pair, and it would basically look like this. Okay, and if you simply computed this, you would have got the answer and symmetrized and stuff, and that is the claim. Okay, instead of doing anything else. This goes as 1 over c squared because of the projectors which have been inserted. Okay, and we, just for simplicity's sake, we'll forego symmetrization, and it can be shown that the leading piece is in 1 over c only requires this kind of single stress tensor exchange. Of course, if you put more stress tensor exchanges, it will be further subdominant in 1 over c, but it's a bit of a computation to show that it would be that way, but we can show it. Now, simply using the fact that t tilde is derivative of epsilon, you can write this kind of an integral, which is basically divergence acting on x3, x5, t0 to be x3, x5 expectation value b135. Okay, this is the kind of, so if you look at 41, this is exactly what we are trying to do. We are going to take t tildes, write them as del bar epsilons, and shift those del bars on the t's. Okay, the indices indicate what's it called, the space-time components. Okay, so t minus 1 stands for x minus 1, and it's just a shorthand. So that derivative will only act on t minus 1. And similarly, the derivative emanating from t tilde 0 will only act on t0. Okay, and then you basically make use of, get rid of your integrals by making use of the second equation in 41. That's it. So what you end up finding is that 42, basically the 6-point function can be written like this, where your b12 is this. Okay, it's the same thing. I mean, it's just for this thing. Now, the 4-point function, like b55b, is basically governed by the 4-point function phi 1, phi 2, epsilon 3, epsilon 4, which again basically is controlled by the behavior of phi 1, phi 2, t3, t4 by this differential equation. Okay, so we just need to solve this differential equation. There are other differential equations that come from the relation between t tilde and epsilon, but they will only end up controlling the shadow part, shadow contribution. So you can neglect them. Before going to the 4-point function, you can see that the 3-point function of phi 1, phi 2 with t0 basically takes this form. You can basically show this from first principles. Okay, yeah. So you can keep on using this relations and get it. 45 is a very basic relation. You can prove it by more than one ways by all the basic integral blah blah thing that we have used. It's very basic once you read through it. It's nothing. Yeah. So we make use of the fact that the 4-point function of 2 stress tensor insertions in phi 1, phi 2 can be written out like this. Okay. Again, this is just rearranging of a lot of terms, and it turns out that the epsilon phi 4-point function is basically given by this quantity. Okay, And the only thing which is sort of undetermined over here is this last quantity C2, which is restricted by the which can be shown to be restricted by that last differential equation in the previous slide. Okay, and that restriction is basically this differential equation on C2. Okay, and that basically takes this form, where Z is basically the conformal cross ratio. Okay, and C2 itself can be written in terms of the cross ratio. It is Z34 squared multiplied by A of Z. Okay, so basically you can solve this differential equation. And you can solve this differential equation. You put it in mathematics and it will give you a form, and you can play around with it and stuff. And it looks horrible. And at the end of the day, using this, you can find what is this 4-point function of B's. And the 4-point function of B is the last term, which is actually the important term, which gives the nice behavior, is which is what is discerned from C2. Okay, and this basically yields the final result. You take this, plug it into the final form, you get completely, everything is in terms of these 3 cross ratios, and then you can compare. So what we didn't do is symmetrize and compare it with their answer. But what we did do is simply capture its out of time ordered behavior and stuff, and those things. So this is the right way of doing things. And we claim that if you actually symmetrized it and did the proper thing, you will get that answer, but we have not verified it. Yeah, so this way of doing things, although it's a bit cumbersome and stuff, it's from first principles. Okay, and that's basically it. So we use this result to compute the out of time ordered correlation function, which is basically like you take since there are 6-point functions, there are 3 conformal cross ratios. You use them to map to a thermal cylinder, and you keep both Euclidean and Lorentzian times. As I've already mentioned, if there are more than 2 pairs, then there are more ways of going out of time ordered, and the most chaotic behavior can be found by arranging them on a line and making the nearest neighbors out of time order. Okay, and you arrange it in a out of time ordered manner such that nearest neighbors are out of time ordered. So phi is sandwiched in between, and x and y are on the either sides. And the Rege limit over here is all these cross ratios tending to 1, and you get you can plot these cross ratios and how they cross their branch cuts, and the final answer of the out of time ordered correlator depends upon the special functions that are involved in your conformal block. So it is necessary to know what these special functions are and where their branch cuts are. Depending upon how your cross ratios tend to the Rege limit, they will cross this branch cut and their behavior will change. This will basically give you the exponential behavior once you map it to the thermal bar. So the out of time ordered correlation function basically behaves like this. And this is just the first subleading order is like 1 over c squared, and it there is sinh and the Euclidean times have been put to they're in the denominator over here. And it turns out that for what's it called for this kind of maximally out of time ordered correlation functions, the scrambling time goes as twice t star. Okay. Any questions still here?
Just to ask, with regard to difference with respect to 4-point function ka OTOC, for 4-point function, the exponential growth appears at 1 over c itself, right?
Yes. This is just an artifact of the fact that
right.
That you're looking at n-point function. Yeah.
Right. And so in terms of, say, bulk Witten diagrams, what does equation 54 correspond to? Does it correspond to evaluating bulk loops? Usually, like in the usual 4-point function, you evaluate Witten diagram with the stress tensor exchange, you are bound to see that exponential growth, right? The Rege growth.
Yes.
But here, since it's 1 over c suppressed, is it equivalent to looking at some loop diagram in the bulk?
I don't think so. Actually, it's at the same level of complication as the 4-point function.
I
It's
think
just
it's a graviton vertex suppression, no? You're asking about the extra C, right?
Yeah.
Probably it's extra vertex suppression, like graviton vertex or something.
Okay. Maybe what my question was like, what does it like what you need to compute in as a Witten diagram in the bulk to say see this?
something similar to the star channel, like yeah. So this is also not like explored. Like how will you
Okay.
put it in this thing? But it should be possible.
Okay.
I don't think so. It should be at any other level of complication.
Not loops, you're saying. All right.
See, what happens is that there is this continuous ladder exchanges even in 4-point functions. So
Sure. Yes. That's
if you don't count them as loops, then it's fine. But yeah.
Okay. So I see. So it's not loop. Okay, fine.
I don't think so. This is like you're doing anything like a loop correction, because even in terms of these epsilon exchanges, if you look at this way of looking, there are no epsilon loops. We can actually have epsilon loops over here.
So in equation 39, the psi t doesn't give you the exponential growth. Ut gives you the exponential growth.
Yeah.
I see.
But UT, I don't think so has any kind of loops and stuff. I mean, yeah, though. Yeah, there is some kind of thing that they do, but again, this way of talking does not make much.
But in general, like the bulk picture is not yet clear.
Yeah, that's not clear. To be fair, it's not yet clear. But yeah.
Do we have an idea of how do shadows appear in bulk? Like what's the analog of shadow in the bulk?
No, that's the open question that I'm going to pose. Yeah, this is what it is. I will yeah. So just to bring you back to the bulk, since you're talking about the bulk, you can the out of time ordered business was first done by Shankar and Stanford, and the way they did it is that they had a shockwave in BTZ. Okay, so the shockwave in, like, if you can write in crustal coordinates, non-rotating BTZ is like 55, and you have a shockwave profile along, let's say, the V direction. And it's like delta function supported along the U direction. So like, let's say U is equal to 0 or U is equal to constant, there is a shock. In the delta function support, you also know X. This invokes a back reaction where H mu, G mu goes to G mu plus H mu, where H mu is basically again supported entirely in that U is equal to constant or delta U, multiplied by G of X. This G of X satisfies this linearized Einstein's equation with the delta function support. That's what 57 is. Okay, and this basically dictates the iconal phase shift in your OTOC computation of Stanford and Shankar. Okay. It turns out that you can show that if you took the Casimir equation for the vacuum, for the Casimir equation for the vacuum block in the CFT, okay, and you assumed that that the vacuum block had this kind of a late time behavior, 59. Again, completely an assumption. You cannot do anything of this sort from first principles. If you assume this, and if you assume that the out of time ordered cross ratio behaves in the manner 60, which it does, okay, then you can show that G of X, which is occurring in 59, also follows linearized Einstein's equation. It's an observation that we have made. We do not know how to like sort of link to it to, I mean, from the CFT point of view, but you can clearly see that F, which is the conformal block, is given by the 2-point function of epsilons, and is directly involved in a certain regime, is directly related to the linearized Einstein's equation that was used to solve the shockwave equation. So it definitely means that these epsilon modes have presence in the bulk, but that particular aspect has not been sort of. So the evolution of this reparametrization mode began from the bulk in ADS3. Like you analyze the full space of on-shell configurations and try to like do the coadjuvant orbit business and stuff. But then you can, since you've defined it in d-dimensional CFTs, you can ask the question what it means in the bulk again. Okay, and this is these are some of the interesting questions. It's like what do these reparametrization modes epsilons mean in terms of bulk fields in greater than 3 dimensions. 3 dimensions we will go around in circles. Yeah.
Could you show the previous slide again? Sorry.
Yeah. Yeah.
Yeah, thanks. Yeah. Thank you.
Yeah. So we do not know whether this was noticed before, but we could not find in literature as such that the conformal the Casimir equation in a certain limit basically reproduces linearized Einstein's equation. But yeah, what else can be constrained? Because you get this OTOC behavior from linearized Einstein's equation in the bulk, and the CFT you get it from just the conformal block, which is constrained by Casimir's equation. So there ought to be a relationship between them. Yeah. So open questions which are there are: what are these reparametrization modes in the bulk in greater than 3 dimensions ADS? How do these modes relate to the modes of JT gravity? Because we know that those are reparametrization modes, which are 1D reparametrization modes on the horizon boundary. So if these modes end up capturing the chaotic behavior of CFTs, at least like 2D CFT, of course, because this conformal map from flat to thermal background can only be done in 2D CFTs. Suppose they exist, they do exist in D-dimensional CFTs, and they do give the conformal blocks in even D-dimensional CFTs. Then what do they mean in the bulk? And there is already a JT gravity effective description which explains chaos close to extremality in the near horizon region. So how do these modes connect to that in the near horizon, near extremal limit? Whatever is their description in the bulk, they should also sort of merge into these JT modes and sort of complete the story over there. Now, unlike the 1D reparametrization of the JT gravity picture, what we have is that these modes depend on both space and time. So that is a very interesting fact. You don't have to like dimensionally reduce and stuff. So they give you a much more fuller picture of space-time. You don't have to like dimensionally reduce to get to an effective theory of anything. What that probably may allow is probably can be used to explain the existence of extremal chaos in black holes in ADS greater than 3 dimensions, because that requires you to keep track of what happens in the other coordinates, not just time and the radial coordinate. And what can its flat space limits teach us about flat holography? A possibility is that probably they'll be able to relate chaotic degrees of freedom with BMS charge or something like that. So there are a lot of future directions. I mean, some of them, the last few are quite far-fetched. I do give it to you that, but yeah, these are basically the modes in which you should be thinking chaos in terms of, and the new objects that we could find in the bulk. Yeah. A lot of these things are not known. Yeah. So yeah. Any questions?
Thanks, Rohan, for that very nice talk. Now I will stop recording, and we can discuss as long as you guys want.
Cool.